Let's use the parameterization of the path of the vertical line segment as we solve for the integral of this given integral here. We have the integral of your x dx plus y dy along your path C, which is identified as the vertical line segment from 3,1 to 3,5. The idea of it being vertical segment is supported by your points here, your endpoints. Noticeably, you would see here that your value for your x did not change as your value of y changes from 1 to 5. Clearly, that's an indication of a vertical line segment. By the way, this is of course equivalent to the integral of your p of x dx plus q of xy dy for your path, which is again a vertical line segment. This would tell us here that your p of xy is just x and your q of xy is actually y. It's very important because as we try to solve this using this form, we need to identify the parameterization in terms of t, because in actual form it is p of x of t and y of t times the first derivative of t plus q of x of t y of t times the derivative of your y of t dt from a to b. This is the formula in solving for the integral of the real line integral presented in this manner. Now, the things that we need to do here is, of course, we need to identify a and b. Now, if it's a vertical line segment, it is very clear that what changes would be your y values. Therefore, your a is 1 and your b is 5 as it starts from 1 and ends to 5 in terms of your y value. Okay, because your x did not change. And by the way, even if your function here would be using the parametric form for x and y, since our p is just x, we'll be just needing for the first function x of t, and for the second would be y of t. Okay, that's the next thing we need to identify here, because we are going to use a formula later on. Your x of t, as indicated in the previous examples where our illustrations for the parameterization of vertical segment, is actually equal to your constant, which is just c, because it doesn't change its value. This is equivalent to your c, but your c here is obviously 3, as that is the value that did not change. As for your y of t, it's the t, because the t changes from 1 to 5 from this perspective. With that, what we need more would be the first derivatives indicated here and here. So the first derivative of 3 is 0, and the first derivative of your t is just equal to 1. With all of this already identified, let's now apply it in the formula. You have here the integral from your a is 1 until 5, 1 to 5, okay, and then you will have here p of x and y, but your p is just x. By the way, if this is, say for example, x squared plus y, so you're going to square this and you add it, add the parametric form for y of t, because it is the definition of p of xy. But since it's just originally identified as x, so we will be using only this item here. Hence, you will have 3 times the derivative of your x, which is 0, okay, plus your q, which stands for your y, so that's actually t, the parametric form, times the derivative of y, which is just equal to 1. Okay. By the way, it's not all the time that you're multiplying them. It depends on how you defined your function, or how the function was defined. Since your first function is just x, that's why multiplying to its first derivative, that's why it's 3 times 0. But it's not all the time. We'll have some examples for that as well later on. This dt. So you have here 0 to 5, sorry, that's 1 to 5. Of course, that's 0 plus t dt. Or the integral of t dt from 1 to 5. We know that the integral of t dt is t squared over 2. That's actually here t squared over 2 from 1 to 5, which gives us the value of 5 squared over 2 minus 1 squared over 2. This is equal to 25 halves minus 1 half, which gives us 24 halves, or 12. This is now the value of the integral of the identified function x dx plus y dy along the vertical line segment path from 3,1 to 3,5 using the parametric forms for your vertical line segment and all of these identified details from the given scenario. And of course, all of the techniques, if possible, for integration. Thank you very much for watching.